Every type of planetary boundary explained.
Yeah, ninja-san.
You need Jesus. Go back to
Do I have your attention? The planetary boundaries are a scientific framework. They define the safe operating limits of key Earth system processes. You know, the cycles and flows of the Earth that exchange energy and materials and such, which are critical for supporting ecosystems and human life. Like the water cycle. They regulate the availability of water, nutrients, and energy to sustain Earth. So crossing these limits means we are f***ing these systems too much. Crossing these boundaries means potentially reaching a tipping point. And once we go over that tipping point, there's no going back. Do we know for certain that it is completely over for us once we cross these boundaries? No, of course not, but these are some darn good estimates. It all started in 2009 when a group of international scientists led by one Swedish scientist, Johan Rockström. Their work was published in the journal Nature, and since then they've done a bunch of updates and refinements. And nowadays Johan is still yapping about these tipping points. Go Johan. As of now, the framework identifies 9 critical boundaries, as can be seen here. But what the heck are these? Like, what is novel entities? Take a deep breath, relax, grab some lube, and let's find out.
Climate change.
I actually think that they chose a bad word to describe this one. A better word would be the greenhouse gas effect, because it looks at greenhouse gases in the atmosphere, particularly CO2, and radiative forcing. Radiative forcing is a measure used in climate science to quantify the influence of factors, both natural and human-made, that affect the balance of incoming and outgoing energy in the Earth's atmosphere system. It represents the change in energy fluxes measured in watts per square meter. You see this equation, that's what we're measuring, and we measure it in watts per square meter. So what we're looking for when we measure this is a change in this number caused by atmospheric composition or the surface conditions. We have been able to measure this directly since the 1970s. For times before that, scientists used climate models and proximities and estimates, and 1750 is often used as a baseline to keep an eye on changes in radiative forcing, because that marks the beginning of the Industrial Revolution. So as you can see, greenhouse gases form a warm blanket over the Earth, keeping all the warmth trapped and slowly warming up the Earth more and more. Why do we want to keep an eye on this? Well, because we as humans have a certain environment that we live in. Look around you, this is your environment. That's literally what environment means. It's not some vague concept, it is the place you live in. And we all live in it. And if there's a sudden change in your environment, a change in such a way that you cannot live in it anymore, I think it's good to know about it.
Stratospheric ozone depletion.
Or the thinning of the ozone layer. I think we're actually kind of good with this one. I don't need to spend too much time on it, but it's kind of interesting, so here we go. The ozone layer protects the Earth from ultraviolet light, or the light of the sun. Without the ozone layer, the sun's fierce flames will burn us raw and scorch the Earth beneath its straw. You know, funny thing about ozone, in the stratospheric layer, it protects us from UV. You know, the UV rays blast the O2 that's up there, splitting them into individual oxygen atoms, which in turn bond together again to make O3, or ozone. And when a UV ray hits it again, it splits into an O and an O2 again. And this whole process scatters the energy from the UV rays. That's how it protects us. But you know, funny thing, in the troposphere, the lowest part of the atmosphere, ozone is considered a pollutant. It is harmful to living organisms and a major component of smog. So that's kind of interesting. Ozone up there? Good. Ozone down here? Bad. Anyways, we made a hole in the ozone layer by using chemicals such as CFCs. But then we banded, and now the ozone layer is recovering again. So we good. We don't really need to worry about that one anymore. So yeah, big W for UN interventions. Yay.
Biosphere integrity.
or biodiversity loss. A diverse system is a resilient system. It is a sturdy network that can bounce back from a lot of things. So if we get an ice age, there will be plants and animals that are adapted to that climate, and life will persist. If we have a new heat age, what are we calling the heat age? Does it have a name? It probably does. Then there will be plants and animals that can survive this heat, and life will persist. If you cut too many of the species out, the thing will come crumbling down. With this one, you can clearly see how it's a tipping point, right? Once you hit that critical stage that other species cannot sustain themselves anymore, they die out, which in turn means a bunch of other species cannot sustain themselves anymore, and they die out, and it just starts rolling. Like, we kicked the ball's gone, the ball's down the hill, and at the bottom of the hill is maybe cockroaches or something. I don't know what will survive, but not us. Being at the top of the food chain means you need everything below you. Those things at the bottom, they don't need that much to survive. But we need all of this. Ooh, custom change. To measure this, we look at species diversity. How many different species are there in an ecosystem or a certain area of land? And you can literally measure this by going out there and counting the species. Another type of diversity we want is genetic diversity. RIP white ethnostate, I guess. High genetic diversity allows species to adapt to disturbances and sudden changes, such as, drumroll please, climate change, or diseases. Low genetic diversity weakens the resilience of populations. Another thing the planetary boundary system looks at is functional diversity. So not only do you look at how many different species there are, but you also look at how many different functions these species can fulfill in the ecosystem. For example, different species perform different tasks, such as pollination, predation, nutrient cycling. And the loss of certain functional groups can destabilize an ecosystem. So not only do you look at how many species there are, but also what they do for the ecosystem. And there's a whole bunch of ways to measure this. For example, for plants, you can look at leaf area, root depth, whether or not they fixate nitrogen. And for animals, you could look at things like body size, feeding behaviors, are they a herbivore or a carnivore, metabolic rate, maybe. And all these things, of course, have their own units.
Freshwater use.
Overuse and depletion of fresh water. There are different types of water. Let me show you. I'll show them somewhere. There's gray water, there's blue water, there's green water. So yeah, we use fresh water for human consumption and agricultural demand, mostly. If you use more fresh water than naturally available in your area, you run out. Whoa, what a concept.
Land system change.
And this is the transformation of forests, wetlands, and other natural landscapes into agricultural land or urban areas. Yeah. Are we still keeping attention? Are we still looking? Are we still listening? Close your third tab, okay? I think 2 tabs is enough. You don't need 3. 2 is already too many, but... So here the theory is that we need a certain amount of nature to preserve the biodiversity that we spoke about earlier, a whole complete ecosystem that's able to sustain itself. So yeah, we measured how much land would be needed as nature in order for the entire ecosystem not to collapse. Then we are at 6 out of 9 already, and that's
Ocean acidification.
meaning a decrease in the ocean's pH due to an increase in CO2 absorption. And this affects all types of marine life, and also will probably lead to a tipping point where the oceans are not storing carbon anymore for us, but actually releasing carbon. So that's gonna be a fun one. I actually wrote a whole paper about this years ago and how to maybe fix it. So I'll put it here. Just read this. You're doing great. It's very dumbed down, so legislators can still understand it. It has pretty pictures. Look, I love biology and ecology so much, but I just can't do it. I can't. I need silly little internet breaks where I yell at you guys about community. I am not autistic enough to devote my life to biology. I tried and no one listened. Look at this. I put so much effort into this and I still only got like a C. I made it so easy for them. I even made an implementation plan for each location I picked. I did so much concerta to finish this paper. I don't want to do anymore. Please, just let me complain about phones. It's those darn phones. It's easy. Please, no more. No more. So basically, the more CO2 in the atmosphere, the more CO2 in the oceans as well. Makes sense, right? And that makes the ocean more acidic, which means certain animals cannot survive in the ocean anymore. And because the ecosystem is a web, here, boom, pretty picture, it is very dangerous to let certain species die out. We can't just say, oh, we'll do without these species, because they're all dependent on each other. It's a network. We're all interconnected, baby. Whoa. They need each other and we need them. Because about 2/3 of our oxygen is actually produced in the oceans. And if we make ocean dead zones, we'll get to that, then no more oxygen for us, baby. Let's not make one big ocean dead zone and get rid of our primary oxygen supply, shall we? Okay, that was it for my mental breakdown. Now it's time to move on. We're getting through these. I hope you're still with me.
Atmospheric aerosol loading.
These are the effects of microscopic particles in the atmosphere that affect climate and human health. So these are teeny tiny particles or droplets in the Earth's atmosphere. Aerosols can be natural, such as dust, sea salt, ash, or they can be human-made, such as soot and synthetic sulfates. And atmospheric aerosol loading is one of the 9 planetary boundaries because it has the potential to destabilize the entire Earth's climate system, just like all of these have. Aerosols can change precipitation patterns or reduce solar radiation, and this can have large impacts on ecosystems, agriculture, and water availability. Wow, look at these tiny particles having a big impact. Couldn't say that about your man. So how they do this, huh? Aerosols can directly affect the climate by interacting with sunlight. Some of them, like sulfates or dust, can reflect sunlight back into space, creating a cooling effect. Others, like black carbon, can absorb sunlight, contributing to the warming of the atmosphere. And then there are some indirect effects on climate as well, to do with clouds, leading to less rainfall, and then the rain sort of builds up in the clouds, and then when it does rain, it all comes out at once. I know this sounds fake, but it's real. Trust me, bro. Climate change means so much more than a warmer average temperature. It means different weather patterns, extremer weather. There's desertification of our soils. It means the acidification of our ocean waters, which lead to the dying of our coral reefs, which lead to the dying of our oceans. I don't want to speak all this doom talk, but this is very basic information that everyone should have a grasp on. The thing with Earth systems is that there's a lot of parts in each system, and one reaction can lead to a whole chain of reactions, or more accurately, a network of interactions. Trying to explain these systems is possible, but you will always leave something out, and that doesn't even yet include all the things we don't know yet. Oh, what? Oh yeah, then some human health effects. High concentrations of aerosols can have serious health consequences. These particles can penetrate deep into the lung and bloodstream, leading to respiratory and cardiovascular diseases, as well as premature deaths. We're in deep now, boys.
Biochemical flows.
This one looks at the nitrogen and phosphorus cycle and the disruption of the nitrogen and phosphorus cycles because of agriculture, industrial activity. Plants use nitrogen and phosphorus to grow. and then animals eat these plants to also stay alive. Nitrogen comes from plant material, animals, and get this, lightning. Isn't that cool? Nitrogen is a key component of proteins and DNA, making it vital for living organisms. And because humans are very smart, we figured out that plants use this nitrogen to grow very tall, grow very fast. So what if we synthesize this nitrogen and then put it on the plant and we make them grow fast? And that is exactly what we're doing. However, this has some negative side effects. We also do this with phosphorus. It is another key element that plants need to grow. It is also important for DNA, cell membranes as well, and energy transfer. And phosphorus comes from rocks, animals, and plants. When you use a lot of phosphorus on the land because you're doing an agriculture, then you can cause excess phosphorus to run off into rivers, lakes, any body of water basically. And this is what happens. Because these are growing chemicals, certain plants will grow very, very big, like algae. And that immediately causes biodiversity loss because they push out all the other plants. But also, when these algae start dying again, they take up oxygen out of the water as they decompose, and this creates an ocean dead zone. And this is exactly what it sounds like. The water's dead. There's nothing living there because nothing can live there anymore. An example of this is the dead zone in the Gulf of Mexico, which is caused by nutrient runoff from agricultural fields near the Mississippi River. As far as I know, it's not doing so hot. It's still there. It's still growing. If you are a farmer along the Mississippi River, please do not use synthetic fertilizers. And I think I already explained why ocean dead zones are bad. You know, the oxygen we breathe comes for a large part from the ocean, and also if a lot of species die, we die because we all need each other. We're interconnected, baby. But if you're still not on board with this and you need some more direct effects, then let's talk about reactive nitrogen compounds. Reactive nitrogen compounds mainly end up in our world because of fertilizers and also fossil fuel combustion. And what do these things do? Well, they leach into our drinking water. And then they make our babies blue. Blue baby syndrome. Look at this. I just want to talk about why phones are bad. I don't want to talk about this. Let me get back to complaining about phones, please. Please.
Novel entities.
Again, this name is way too cool for what it actually is, because it's basically just chemical pollution. The release of chemicals, heavy metals, and radioactive materials that can harm ecosystems and human health. Basically, it just says that there are limits to how much poison we can put in our water supplies before we all start glowing. And there isn't really a standardized way of measuring this because each compound has its own unit of measurement. Was that it? For now? What is this all for? The planetary boundaries can show us when we need to adjust our behavior. And one of the ways of adjusting our behavior is by making and enforcing policies. So it can serve as a scientific guide for policymakers. Companies and industries can use it to assess their environmental impact and make sure they do not push beyond these limits. For example, industries can adopt circular economy principles. Now, stay eco, stay connected, and stay pretty. Thank you, JJ, for making the blobs. They're very cute. I really like them. If you enjoyed this video, then maybe go click on some of the other videos I made. You might like them. Also, if you want to support me, I have a Patreon. Thank you so much for paying attention, for educating yourself a little bit. Stay eco, stay offline, and stay pretty.